A vast, empty ocean stretches in every direction with no land in sight. Your survival depends entirely on reading a map written in the stars. This was the daily truth for medieval navigators, masters of celestial navigation, who turned the night sky into a guide. By the end of this story, you will understand the precise techniques that let humans conquer the planet's greatest wilderness. How did a single stationary star become a fixed point in a spinning sky? And what secret tools turned starlight into a measurable grid? At its heart, this is a tale about our oldest relationship with the universe. What does it mean to place your trust in something as distant as a star? For a sailor under the open sky, the sun was the first and most reliable teacher. Its daily journey from east to west painted a simple, powerful line across the heavens, a line that meant everything when every wave looked the same. Long before the complex charts and instruments we associate with medieval navigation, the fundamental act of finding direction began with this single, burning point. Observers from ancient Egypt to the Greek philosophers had mapped its rhythms, understanding that at the precise moment it reached its highest point in the sky, it pointed directly south in the northern hemisphere. This moment, local noon, gave sailors a true north-south line, a celestial meridian they could trace in their minds across the featureless sea. It was an ancient compass written in light, a starting point from which all other calculations could begin. This practice, passed down and refined over countless generations, was not about pinpoint accuracy over vast distances, but about establishing order. It answered the most basic, vital question: which way am I facing? The sun's predictable arc provided a daytime anchor, a reassurance that even on the open ocean, you were not completely lost. You had a reference to the world's spin, but this solar guidance came with profound limitations. Cloud cover could erase it in an instant. The sun's path shifted with the seasons, rising and setting at different points along the horizon, requiring deep knowledge to interpret correctly. And as the sun dipped below the waves, it took this primary reference with it, plunging the world into a darkness that could feel absolute. This daily disappearance underscored a relentless truth for early mariners: the sun was a magnificent but part-time guide. Its very absence highlighted the need for another, more constant system. The stage was set by the sun's retreat, the need established by its limitations. So as daylight faded, the navigator's gaze would lift, searching the deepening blue for the first faint pinpricks of light. The real map was about to be revealed. The night sky that greeted these sailors was not a random scattering of lights. It was a vast, intricate machine, understood through the lens of celestial spheres. Picture, if you will, the entire cosmos as a set of nested, transparent shells surrounding the Earth, each one rotating with perfect, divine regularity. The outermost sphere held the fixed stars, pinned to its surface like jewels on a slowly turning dome. This was the foundational map of medieval cosmology, a model described by scholars like Ptolemy and embraced by navigators because it offered something priceless: predictability. In this orderly universe, certain stars never wavered in their relationship to each other. They were fixed. This constancy transformed them from mere points of light into trusted landmarks. A sailor would learn to recognize key patterns: the steadfast bowl of Ursa Major, the Great Bear circling the North Star in the northern heavens, or the distinctive cross of the Southern Cross guiding those in southern latitudes. These were not just pretty shapes, they were signposts. Their position in the sky, and crucially, whether they dipped below the horizon or remained eternally visible, told a navigator where on the Earth's curved surface he might be. From a specific latitude, a given star would always be seen at the same height above the horizon on a given night. This was the profound practical insight born from an abstract model. The belief in a structured, knowable cosmos made the stars something you could truly navigate by. They became the first reliable coordinates in a trackless void, a map written in constellations that felt as permanent as mountains on land. But knowing the map is one thing, reading your position on it is another. To move from recognizing a landmark to plotting a course, sailors needed a way to measure their relationship to these distant guides. They needed to translate starlight into numbers. This is where the sky truly became a tool. Among all the fixed stars, one held a unique and almost magical position. For sailors of the Northern Hemisphere, the star we call Polaris, the North Star, was the anchor of the entire celestial map. It did not behave like the others. While every other star wheeled grandly around the sky throughout the night, tracing great arcs from east to west, Polaris held its ground. It appeared nearly motionless, a pivot point around which the whole cosmos seemed to turn. This was because it sat almost perfectly in line with the Earth's rotational axis, directly above the North Pole. That single, stationary point of light changed everything. It transformed the night from a beautiful spectacle into a functional instrument. A navigator could now look up and know with absolute certainty where true north was. Simply finding the direction was a monumental advantage, but the true genius came from what they did next. They began to measure their distance from it. The key was not just Polaris's direction, but its height. If you stood directly at the North Pole, Polaris would be directly overhead at what we call the zenith. If you sailed south, the star would appear to sink lower in the sky, closer to the northern horizon. This angle between the star and the horizon, known as its altitude, was a direct reflection of your latitude on Earth. It was a cosmic yardstick. At the equator, Polaris would sit right on the horizon. Halfway to the pole, it would be halfway up the sky. This relationship was beautifully, mathematically consistent. To measure this angle, navigators developed beautifully simple tools. The camel, used by Arab sailors, was a small wooden rectangle on a string. By holding the rectangle at arm's length and aligning its top edge with Polaris and its bottom edge with the horizon, the length of string pulled taut to the navigator's eye created a fixed angle. Different knots on the string corresponded to known latitudes, like a primitive but effective slide rule. The cross-staff, a later refinement, used a sliding crosspiece on a calibrated staff to achieve the same goal with slightly more precision. With nothing more than a piece of wood, a string, and this one steadfast star, a sailor could answer the most critical question: how far north or south am I? This was a quiet revolution in human mobility. Viking navigators crossing the treacherous North Atlantic relied on this principle. Their sunstones for cloudy days are famous, but on clear nights, Polaris was their unwavering guide. Arab traders navigating the Indian Ocean and beyond used the camel to chart consistent courses along known latitudes, turning risky exploration into repeatable trade. The psychological impact cannot be overstated. In a world of heaving waves and howling winds, here was a point of perfect calm. The sky spun, the ship rolled, but Polaris remained fixed. It was a promise of stability in chaos, a literal guiding light that offered not just direction, but a sense of place in the immense, trackless ocean. It turned the abstract concept of latitude into something you could see and measure with your own eyes. Yet, for all its constancy, Polaris had one profound limitation. It was a northern star. For those who sailed into the waters below the equator, it slipped forever beneath the horizon, taking its celestial anchor with it. This presented the next great puzzle for the medieval navigator. If the North Star vanished, what then became your fixed point in the southern sky? The southern sky presented a profound and unsettling mystery. Without a single fixed pole star to anchor them, navigators venturing below the equator faced a celestial map that seemed to spin freely, offering no obvious center. Yet, the human drive to find patterns is relentless. In the absence of one guide, they learned to navigate by the motion of many. They turned to entire constellations, watching how they rose and set, and tracked the circular paths of bright stars like Canopus or the two pointer stars of the Southern Cross. By observing where these celestial bodies culminated or reached their highest point in the sky, and carefully measuring their altitude above the horizon, skilled navigators could still deduce their latitude. It was a more complex dance, requiring a deeper mental map of the sky's nightly rotation, but it proved a crucial truth. Our need to navigate would not be thwarted by the cosmos's design. We would simply learn a more intricate set of steps. This challenge in the South underscored the universal principle driving all celestial navigation, the necessity of measurement. Knowing a star's position was theoretical. Turning that position into a number you could plot on a chart was everything. This gap between observation and data demanded not just knowledge but invention. The mind of the navigator had to extend into the physical world through tools born from equal parts astronomy, carpentry, and sheer necessity. The first of these tools were marvels of elegant simplicity. Take the camel, used for centuries by Arab and Indian ocean sailors. It was nothing more than a small, rectangular wooden card, often not much larger than a bookmark, with a knotted string tied through its center. Its operation was a lesson in bodily geometry. The navigator would hold the string at his eye, then extend his arm fully, letting the card dangle at the end. He would then slide the card along the string until its bottom edge aligned with the horizon and its top edge just touched the star he was sighting, often Polaris. The knot that then rested at the corner of his eye indicated a specific angle, and sailors would tie different knots for the latitudes of familiar ports. It was a personal instrument calibrated to a man's own arm length, a direct physical translation of angle into memory and touch. For greater precision, European navigators later adopted the cross-staff. Imagine a long primary staff, marked with degrees, and a shorter crosspiece that could slide along it. The navigator would place one end of the main staff against his cheekbone, then slide the crosspiece back and forth until its lower end met the horizon and its upper end touched the star. Reading the scale on the staff where the crosspiece sat gave the altitude angle. It was a more standardized tool, but using it on the deck of a moving ship was a feat of concentration. Balancing on shifting planks braced against the wind, you had to keep the horizon steady in your sight while a star danced above it, all to capture a single, fleeting number. The mariner's astrolabe, a heavy bronze disc marked with degrees and a pivoting sighting rule called an alidade, attempted to bring more stability. You would suspend it from your thumb to let it hang vertically, then rotate the alidade to line up with the star and read the angle from the scale. But its weight, meant to counteract motion, made it cumbersome, and in strong winds it could swing like a pendulum, rendering a precise reading nearly impossible. Each of these instruments, from the humble knotted string to the ornate bronze disc, shared a common purpose. They were bridges. They spanned the immense, silent gulf between the human observer on a tiny, tossing ship and the cold, distant points of light in the eternal night. Every squinted measurement, every noted degree was an act of connection. It was a sailor whispering a question to the universe and, with careful hands and patient tools, writing down the answer. This hard-won data, this number pulled from the stars, was the final key. It told you your latitude, your north-south line on the globe, but the ocean is a two-dimensional plane. Knowing how far north you are is useless if you do not also know how far east or west you have traveled. The stars could give you one coordinate, but for the other, medieval navigators had to turn their attention from the heavens to the deep, mysterious currents of the sea itself. With a number pulled from the stars, the navigator now faced the practical puzzle of the sea. Knowing your latitude was like knowing you were on a specific rung of a vast, invisible ladder. The next step was deciding how to move along that rung. This gave rise to one of the most elegant and pragmatic strategies in the history of exploration, a method known as latitude sailing. Think of the ocean not as a blank page, but as a sheet of graph paper with the lines of latitude running horizontally across it. Once a captain knew the latitude of his destination port, his goal became beautifully simple. He would sail his ship north or south until his celestial measurements told him he had reached that exact parallel. Then he would turn the helm, point the bow due east or west, and simply follow that line. It was the maritime equivalent of finding the right street, then walking straight down it until you reached your door. This method was a brilliant workaround for the era's greatest navigational limitation: the utter impossibility of accurately determining longitude at sea. Longitude, your east-west position, required knowing the precise time difference between your location and a fixed point, like your home port. Without an accurate sea-going clock, that knowledge was pure guesswork, often leading to catastrophic errors. Latitude sailing sidestepped this problem entirely. It accepted the limitation and built a whole system of travel upon the one coordinate the stars could reliably provide. The ocean transformed from a terrifying void into a network of known pathways, a series of celestial highways. You can see this principle etched into the routes of history. Portuguese caravels probing down the west coast of Africa in the 15th century were masters of this technique. Their captains were not blindly striking out into the Atlantic. They would sail south to a known latitude, perhaps that of the Cape Verde Islands, then turn east to make their landfall. On the return journey, they would sail north to that same familiar parallel before turning west for the final run home. Each successful voyage added another horizontal line to their mental chart, another celestial road they could travel with growing confidence. It was a slow, deliberate, and immensely powerful form of cartography, drawn not with pen and parchment, but with keels and constellations. Yet, for all its genius, this method held a hidden cost. Following a parallel of latitude is not the shortest distance between 2 points on a globe. That would be a great circle route. It could add days or even weeks to a journey, a tax paid in hunger, thirst, and the relentless anxiety of an extended voyage. The navigator, therefore, lived in a constant state of calculation. He balanced the safety of the known celestial highway against the perilous temptation of a shorter, uncharted path. Every decision was a gamble with the lives of his crew and the fate of his mission. This was the navigator's eternal tension, caught between the clean, certain lines of the stars above and the messy, unpredictable reality of the world below. And while the heavens provided a north-south guide, the sea itself whispered clues about the east-west journey, if one knew how to listen. Yet the stars offered only half the answer. For all their precision in measuring north and south, they fell silent on the question of east and west. Longitude remained the great unsolved puzzle of the age, a ghost in the navigator's calculations. Without a way to pin down this second coordinate, every voyage into open water was an act of faith layered over guesswork. This profound limitation forced sailors to master a different, more desperate kind of art. They called it dead reckoning. Think of it as navigation by memory and momentum. Starting from a known point, perhaps a last-sighted headland or a celestial fix for latitude, the navigator would then plot his future course based on 3 fragile estimates. Direction came from the compass, time was measured by turning hourglasses, their sand a slow, granular count of the passing day, and distance, the most elusive factor of all, was guessed by observing the ship's wake, the feel of the wind on the sails, and a deep, intuitive sense of the vessel's speed through the water. He would mark each day's estimated progress on his chart, drawing a line of presumed position further and further into the unknown. It was a continuous chain of educated guesses, each link susceptible to error. A current running stronger than expected, a storm that blew them subtly off course for hours, a slight miscalculation in speed, all these tiny errors would compound day after day, week after week. Like a whisper passed down a long line of people, the message of your true location would grow distorted with each step away from the source. This is why that single, star-derived latitude fix was so profoundly precious. Dead reckoning was the fragile thread stretching out behind the ship, a narrative of where you thought you were. The stars provided the occasional, vital knot, a moment of absolute truth that kept the entire story from unraveling. A navigator might sail for weeks by reckoning alone, his plotted position creeping further east than reality. Then, on a rare clear night, he would take a measurement of Polaris or the Southern Cross. The altitude would tell him his latitude, which he already knew from his reckoning, but the act of observing the star's position along that latitude line could sometimes hint at a longitudinal error. More directly, if the star's measured height did not match the latitude his dead reckoning claimed he was on, the shock was immediate and corrective. The star did not argue, it stated a fact: your thread has drifted. You are not where you think you are. The consequences of ignoring these celestial corrections were the stuff of maritime nightmares. A ship relying solely on dead reckoning, aiming for a narrow channel or a small island group, could find itself dozens of leagues off course, with supplies dwindling and morale collapsing. The ocean was littered with the ghosts of such miscalculations, so the navigator lived in a state of respectful tension between two worlds. He used the art of dead reckoning to navigate the continuous present, making his best guess with the tools at hand. And he awaited the science of the stars, those fleeting moments of cosmic clarity, to anchor him back to reality. It was a humble acknowledgement that human estimation, no matter how skilled, needed an anchor in something beyond itself. The stars were that anchor, the fixed points in a spinning, slipping world, and as voyages stretched further, pushing beyond the familiar lanes of latitude sailing, the hunger for a more complete solution grew. This hunger would eventually drive a quest not for a better star chart, but for a perfect clock. But the sun was not as simple as it first appeared. For all its reliability as a daytime marker, it presented a seasonal complication that could quietly unravel a navigator's careful work. The sun does not follow the same arc in the sky every day of the year. In summer, it rides higher, tracing a longer, grander path. In winter, it slips lower, its arc shorter and more subdued. This north-south drift of the sun's path is called its declination. To a sailor trying to measure his latitude by the sun's noon altitude, this drift was a source of potential error. If you measured the sun's height on a summer day and used the same calculation you would in winter, you could believe you were hundreds of miles from your true position. The sun, your trusted guide, was subtly lying to you with the turning of the seasons. Correcting for this solar drift became one of the great intellectual projects of the medieval world, a bridge between pure astronomy and practical survival. In observatories from Cordoba to Toledo, Islamic and later European scholars meticulously tracked the sun's yearly journey. They produced vast, beautiful tables like the Shrouded Tables compiled in the 11th century, which catalogued the precise position of the sun and stars for every day of the year. These were not just academic exercises, they were essential software for the navigator's mind. A captain or pilot would carry with him, either in memory or in a precious handwritten book, these declination tables. At local noon, when the sun reached its peak, he would take his measurement with his cross-staff or astrolabe. That raw number gave him an apparent altitude. Then he would consult his tables for that specific calendar day. The tables told him how many degrees north or south of the celestial equator the sun was positioned on that exact date. By applying this correction, adding or subtracting that declination value from his measured altitude, he could arrive at his true latitude. It was a two-step calculation that transformed a variable star into a precise instrument. Think of it as calibrating your watch for daylight saving time. You know the sun says it's noon, but your tables tell you the cosmic clock is set a little differently today. By applying that correction, you sync your local observation with the universal system. This knowledge was power. It meant a Portuguese caravel could sail the Atlantic in July or January and still trust its solar readings. It meant an Arab how could depart from Aden on a predictable schedule, knowing its noon sun sight would be mathematically true regardless of the month. Mastering solar declination moved navigation from the realm of rough, seasonal estimates into the domain of repeatable, year-round science. It acknowledged a profound truth about the cosmos, that its movements were complex, but they were not random. They were predictable, measurable, and could be written down in a table. This turning of celestial motion into usable data may be the quietest revolution in the story of exploration. It required no new ships, no grand expeditions. It required only the patient, collective work of watching, recording, and sharing knowledge across generations and cultures. The navigator, alone on his deck with a wooden instrument, was now connected to a chain of observers that stretched back centuries. He was not just reading the sun, he was reading a collaborative human story written in numbers, a story that told him exactly where on Earth he stood. The stars held more than just position, they held time. While a single star like Polaris could tell you where you were, the grand procession of constellations across the night sky told you when it was. For cultures whose survival was tied to the sea, this celestial calendar was as vital as any chart. In the Mediterranean, the rising of the constellation Orion in the evening sky was a herald of winter, a signal to cautious sailors that the time for fair weather coastal trading was ending and the season of more perilous, open sea voyages might begin if one was brave enough. Further east, the appearance of Scorpius low on the horizon marked specific periods in the annual cycle for Arab and Indian Ocean traders. These were not arbitrary associations. The movement of these sprawling star patterns was locked in rhythm with the Earth's journey around the sun, and thus with the turning of the seasons on the water. They announced the shifting of the great monsoon winds, the engine of trade across the Indian Ocean. To see a certain constellation culminate or reach its highest point at dusk was to read a memo from the atmosphere itself. It meant the winds were about to reverse, and a fleet laden with spices, silks, or ivory needed to be ready to catch that celestial tide. This knowledge transformed astronomy from a tool for space into a tool for timing. The stars told you not just the route but the schedule. They dictated the rhythm of entire economies, creating windows of opportunity that opened and closed with cosmic precision. No culture mastered this integration of sky and sea more profoundly than the Polynesian navigators of the Pacific. Their system moved beyond using stars as mere markers. They built a mental model of the entire moving sky. They conceived of a star compass, not a physical object but a conceptual one. Imagine the horizon as a great circle divided into 32 houses like segments of an orange. Each house was named not for a direction like north or south, but for a specific bright star that rose or set in that precise spot. The navigator would memorize this compass, knowing that as one star-set house dipped below the horizon at dusk, another star-rise house would be appearing opposite it. His canoe became the fixed center of a turning star dome. By keeping a mental track of which star house was rising, which was setting, and which was directly overhead, he could hold a course through nights and days of clouded skies, dead reckoning elevated to an art form rooted in deep celestial memory. This was navigation by feel, by rhythm, by being embedded within the environment rather than just measuring it. The sky was not a map to be consulted. It was a living, breathing part of the voyage itself. The stars, in their eternal cycles, whispered the secrets of timing, telling generations of sailors the ancient, vital truth that to journey wisely, you must understand not only the path but the moment. But the greatest celestial bodies were not always points of light. Sometimes the most critical guide was a great gray disk that reflected the sun's borrowed glow. The moon governed a realm the stars could not touch, the rhythmic pulse of the sea itself. For a navigator finally approaching land after weeks in the deep ocean, the moon's phases were not just a celestial calendar, they were a matter of survival. A mistake in timing could turn a safe harbor into a death trap of crashing waves or a hidden maze of sandbars. Predicting the tides, those immense breadths of the ocean drawn by the moon's gravitational pull, became a final, essential layer of celestial knowledge. This was not navigation for positioning, but for transition, the delicate shift from the open wilderness back into the world of men. Observant sailors across the globe noticed the patterns. A full moon or a new moon, when the sun and moon aligned with Earth, brought the strongest tides, the spring tides, with the highest highs and the lowest lows. The quarter moons produced the gentler neap tides, but knowing this basic cycle was just the beginning. The local character of a tide, its precise timing and height at a specific river mouth or rocky channel, was unique, shaped by the shape of the coastline and the depth of the seafloor. This hyper-local knowledge could not be found in any star table written by a scholar on land. It lived in the oral traditions of the pilots, the coastal specialists who guided ships through the final, treacherous mile. They encoded this wisdom in simple rhymes and chants, easy to remember and pass down. A medieval English pilot might recite, "A flowing tide, wait outside, a full moon's ebb will grind your web," a warning not to enter a certain estuary on a strong outgoing tide lest your ship's nets, or worse, its hull, be torn apart on the bottom. Polynesian navigators had charts that linked the moon's appearance with the behavior of specific currents around their home islands. This was practical astronomy at its most intimate. It linked the moon's position relative to familiar stars, its age in the night sky, directly to the feel of the water beneath the keel. A navigator would note the moon rising near the bright star Aldebaran in Taurus and know that in 3 days' time, the tide at a particular landing would be just high enough to cross the reef at dawn. Mastering this rhythm was the culmination of the navigator's art. It meant understanding that the cosmos did not just offer a static map, but a dynamic force that physically moved the world. The moon pulled the water, and the water lifted or grounded your ship. To ignore this connection was to see the sky and the sea as separate realms. To embrace it was to navigate holistically, to read the universe as a single, interconnected system where light, gravity, and salt water were all part of the same conversation. After trusting the stars to cross the void, you now had to trust the moon to let you come home. The moon's silent pull on the tides was a force felt in every port, but to truly master the open ocean required a different kind of gravity, the intellectual gravity of a scientific revolution. While European sailors were still cautiously hugging coastlines, a parallel maritime world was thriving under a canopy of stars meticulously mapped by Arab and Persian scholars. This was not merely an improvement in technique, it was a complete reimagining of navigation as a formal, teachable science. At the heart of this revolution was the humble Astrolabe, a device known to the ancient Greeks. In the hands of Islamic scholars, it was transformed. The mariner's astrolabe, a heavier, simplified version of the intricate planispheric model, was engineered for the pitching deck of a ship. Its pierced design allowed the wind to pass through, reducing its swing, and its weight gave it the stability needed to take a reading from a star or the sun. This was technology democratized for the sailor, taking a complex instrument of the scholar's study and hardening it for the salt spray of practical use. But the tool was only as good as the data it measured. Here, the scholars of the Islamic Golden Age made their most enduring contribution, the creation of precise and voluminous astronomical tables, known as Zij. These were not simple star charts. They were massive computational works that catalogued the movements of the sun, moon, planets, and fixed stars with unprecedented accuracy. The Shrouded Tables, compiled by a group of astronomers in Muslim Spain, and later the Ilkhanic tables produced in Persia became the standard reference for centuries. They provided the critical corrections for solar declination and the positions of navigational stars for any given day and night of the year. A navigator from Aden to Malacca could consult the same tables, speak the same numerical language, and trust the same celestial coordinates. This shared dataset created a common framework across the vast Indian Ocean trade network. Knowledge became portable, repeatable, and most importantly, verifiable. It turned navigation from a secretive, guild-protected art into a systematic practice that could be learned from a book. The ultimate expression of this was the Kitab al-Fawaid, or Book of Useful Information, written by the 15th century navigator Ahmad ibn Majid. This was not a dry academic text. It was a comprehensive sailor's manual, blending poetic descriptions of the stars with brutally practical advice on winds, currents, coastlines, and the use of the camel. Ibn Majid did not just list stars, he told you which ones to use for which season and from which port, weaving rigorous astronomy with generations of hard-won experiential knowledge. This systematic sharing of information created an invisible web of understanding. A ship's pilot from Oman could sail to the Swahili coast of East Africa or the spice ports of Indonesia and find a community of traders and sailors who understood the same principles, who consulted similar tables, and who measured the sky with the same intent. The Arab contribution was this: they provided the grammar. They gave the scattered dialects of celestial observation a unified syntax and vocabulary. They transformed a collection of local star stories into a global science of the sea, proving that the sky could be a shared textbook and the ocean a common classroom. Yet the southern sky refused to offer a single, solitary guide like Polaris. Below the equator, the familiar North Star slipped forever beneath the horizon, taking with it that precious fixed pivot point. In its place, navigators found a sky that seemed to whirl freely, a celestial dance without a clear center. This presented the ultimate test of the principles they had honed in the north. Could their methods survive in a mirror image world? The answer lay not in one star, but in a distinctive pattern of four. The constellation crux, the Southern Cross, became the new anchor. Its compact, bright diamond shape was unmistakable, a celestial signpost that never set for observers across much of the southern hemisphere. Portuguese explorers pushing down the west coast of Africa in the late 15th century were among the first Europeans to document its navigational use with meticulous care. They faced a new puzzle. The Southern Cross itself rotates around the south celestial pole, but that pole is marked by no bright star. To find it, they had to learn a new technique. They used the two pointer stars of the nearby constellation Centaurus, Alpha and Beta Centauri. By imagining a line extending from the top to the bottom of the cross, and another line perpendicularly bisecting the distance between the two pointers, navigators could mentally project the intersection of these lines to locate the approximate position of the south celestial pole, a blank spot in the sky around which everything else turned. This was navigation by geometry and imagination. It required building a new mental map, one where the fixed point was an invisible coordinate deduced from the relationships between visible lights. It proved a profound truth about human ingenuity. We do not need the universe to provide a ready-made beacon. We can construct our own guide from the patterns we observe. Mastering this southern sky was not an academic exercise. It was the key that unlocked the globe. Once Portuguese captains could confidently determine their latitude using the Southern Cross, the Great Barrier of the African continent could be rounded. They could sail into the Indian Ocean, connecting directly to the spice routes. Furthermore, understanding southern celestial navigation allowed for the daring westward crossings of the Atlantic's lower latitudes, opening the sea road to what would become Brazil. The Southern Cross transformed from a curious southern pattern into a symbol of a connected world. It stood as testament that celestial navigation was a universal language. The principles of measurement and observation forged under the North Star could be translated and applied under any sky. Human curiosity, it seemed, was not bound by hemisphere. We would simply learn to speak to the stars in their local dialect, whether they hung over icy northern fjords or the warm, vast waters of an uncharted southern sea. But the sun could vanish for days behind a veil of cloud and mist. In the gray, featureless light of the North Atlantic, where the horizon dissolved into the sea and the sky offered no shadow, a Viking navigator faced a sensory void. Norse sagas whisper of a tool for such moments, a solarstein, a sunstone. It was said that with this stone, a skilled user could find the hidden sun's position even on a completely overcast day. Modern research suggests this may have been a piece of Iceland spar, a transparent calcite crystal with a remarkable property. It polarizes light, meaning it can filter the scattered sunlight that penetrates cloud cover. By rotating the crystal and observing changes in brightness or patterns within it, a navigator could potentially deduce the direction of the sun's hidden disk. The exact method is lost to history, a subject of intense debate among scholars and experimental archaeologists. Yet, whether the sunstone was a precise instrument or a more general aid, its legend is profoundly revealing. It represents the absolute refusal of these navigators to be blinded. When the primary celestial reference was stolen by the weather, they turned to the physics of light itself. They sought not a new star, but a way to see the ghost of the sun, its invisible signature written in the polarized glow of the overcast sky. This pragmatic innovation underscores a vital truth about medieval wayfinding. It was never a single system. It was a layered, adaptive toolkit. On a clear day, you used the sun's arc. On a clear night, the wheel of stars. When both were obscured, you might turn to a piece of crystal in your palm, reading the sky's hidden geometry through a lens of rock. You observed the flight paths of birds known to nest on land, the subtle shift in ocean swell patterns rebounding from a distant coast, the color of the water, and the taste of the wind. The sunstone, myth or reality, symbolizes this relentless, multi-sensory engagement with the world. Navigation was not just astronomy, it was a dialogue with every element. It was the understanding that information was everywhere, in the air, the water, the light, and the life around you. The goal was constant, to piece together a coherent picture from whatever clues the world deigned to provide. The quest to see the unseen was the navigator's deepest drive, pushing them beyond simple observation and into the realm of interpretation and inference. The vast Pacific presented a challenge of a different scale. Here, the distances between islands were not measured in days, but in weeks of sailing across an ocean with no continental shores, no familiar currents to follow. In this watery desert, the Polynesian navigators performed what seemed like magic. They crossed thousands of miles of open sea in double-hulled canoes, reaching specks of land scattered across an area larger than any continent. And they did it without a single metal instrument, without a written chart, without a compass. Their technology was not built from wood or bronze. It was etched into memory, song, and an intimate, living relationship with the star paths. For a Polynesian navigator, the horizon was not a blank line. It was a compass rose etched with light. They had perfected a mental model called the star compass. Imagine the entire circle of the horizon divided into 32 houses, like segments of an orange. But each house was not named for a direction like north or south. It was named for a specific, bright star that rose from that exact point on the eastern horizon, and its counterpart that set in the opposite western house. The navigator had memorized hundreds of these stars and their precise gateways. He did not sail toward a point on a map. He sailed by keeping his canoe positioned within a specific star house. As the night progressed and the earth turned, One guiding star would rise too high and another from an adjacent house would take its place. The navigator was constantly updating his mental picture, his canoe the fixed center of a grand, rotating star dome. This was not passive observation. It was active, dynamic participation in the cosmos's motion. Within this framework, one technique stood out for its elegant precision: the use of the zenith star. Every island has a star that passes directly overhead at the zenith when viewed from that island's latitude. For a navigator aiming for a specific atoll, that star was a celestial address. His goal was not to follow it, but to sail toward the place where it would eventually stand directly above him. At the beginning of the voyage, that zenith star would appear ahead of the canoe, low on the horizon. As he sailed, he would watch it climb higher and higher in the sky. His course was correct as long as the star continued its ascent toward the zenith. If it began to drift to the left or right, he knew the currents or wind were pushing him off track, and he would correct. Reaching his destination meant arriving at the precise moment that star burned a hole in the sky directly above his head. This required an encyclopedic memory, knowing which zenith star belonged to which island across the vast ocean. It also demanded relentless mental calculus, factoring in the canoe's speed, the push of unseen currents, and the steady march of the star itself. He was solving a complex navigational equation in his mind, with the sky as his only calculator. This knowledge was not kept in books. It was a sacred trust, passed down through generations in chants and stories, taught through years of apprenticeship on the open sea. A master navigator, or PWO, held a library of the sky in his mind. He could feel the rhythm of the swells, taste the salinity of different currents, read the flight patterns of birds, but the star paths were his primary guide. His canoe was a vessel of culture, carrying not just people and supplies, but an entire system of understanding built from millennia of observation and courage. What they achieved demonstrates a profound truth about technology. Sometimes the most advanced system is not a physical tool, but the cultivated human mind itself, trained to perceive patterns invisible to others, to hold a map of the cosmos in memory, and to find a way home by the slow, sure climb of a single star. The mental star maps of the Polynesian navigators were a living, breathing system, but they remained locked within the memory of a single master. For knowledge to travel as freely as the ships themselves, it needed a physical form. This is where the story of celestial navigation meets the page, not in books of astronomy, but in the birth of the sea chart. The most famous of these from the medieval era are the Portolan charts, and they hold a beautiful secret. At first glance, they seem to have nothing to do with the stars. They are breathtakingly detailed maps of coastlines, from the Black Sea to the Atlantic, crisscrossed by a spiderweb of straight lines radiating from intricate compass roses. But every single line on that parchment is a silent record of a celestial observation. These charts were not drawn from a god's eye view. They were painstakingly compiled from the logbooks of countless pilots, each of whom had spent a lifetime measuring the sun's noon altitude and steering by the night stars. When a pilot sailed from Genoa to Alexandria, he was not just traveling, he was collecting data. He would note the bearing, the direction he held by watching the North Star's relation to the mast, and he would estimate the distance through days of dead reckoning. Back on land, a chartmaker would take these hundreds of logged courses, these star-derived bearings and estimated leagues, and weave them together into a single, coherent picture. The web of lines, called room lines, is the direct translation of those courses. To sail from one port to another, a mariner would simply find the line connecting them, note the compass direction it indicated, and set his course. The chart itself became the intermediary, a repository of collective stellar experience. It meant a young sailor no longer had to personally know the zenith star of every island. He could inherit, on a sheet of vellum, the hard-won knowledge of generations who had measured the sky. This was a monumental shift from oral tradition to recorded science. The Portolan chart did not show the stars, but it was fundamentally anchored by them. Every confidently drawn coastline, every accurately placed island, was ultimately verified by someone, somewhere, looking up and measuring their place in the cosmos. The chart was the answer to the stars' question, a permanent, shareable reply written in ink. It turned the private art of the navigator into a public utility, democratizing the ability to traverse the known world. Yet, for all their precision in the Mediterranean and European waters, these charts revealed a telling limitation. Coastlines faded into vague speculation at the edges of the explored world, because no star sightings existed to correct the guesswork there. The Portolan was a map of knowledge, and its blank spaces were a silent testament to the frontiers where the guiding stars had not yet been measured. Even the clearest star sight held a hidden distortion. The air itself, the very medium through which the navigator gazed, played a subtle trick on the light. A star near the horizon never appeared in its true geometric position. It was always lifted slightly higher by the thick blanket of Earth's atmosphere. This bending of light, a phenomenon we now call atmospheric refraction, meant every measurement contained a small, consistent error. The lower the star, the greater the lift. For a star observed at the horizon, this shift could be more than half a degree, a massive error in terms of nautical miles. At the same time, another correction came from the deck beneath the navigator's feet. When he stood on a ship, his eye was elevated above the true sea level. This height of eye meant he was looking down at the horizon, not directly at it. The visible horizon dipped below the true astronomical horizon, creating another angular discrepancy known as dip. Both of these effects, refraction and dip, conspired to make a star appear higher in the sky than it truly was. An uncorrected measurement would always place the ship farther north in the northern hemisphere, or farther south in the southern hemisphere than it actually was. It was a systematic drift written into the physics of observation. The masters of the craft did not need to understand the science of optics to see its consequence in their landfalls. Through long experience and comparison, they learned to anticipate the sky's gentle deceit. They developed mental rules, passed down a Chinese letter, or simple rhymes and formulas. An Arab navigator using a camel might know to pinch the string just a fraction shorter when sighting a low star. A European pilot with a cross-staff might instinctively hold the instrument a certain way, or subtract a few minutes of arc from his reading based on the star's altitude and the estimated height of the ship's deck. This was not written in any formal table. It was knowledge carried in the body and the mind, calibrated by a lifetime of comparing celestial predictions with the hard reality of a coastline appearing on schedule. This attention to subtle environmental detail marked the difference between competence and mastery. It transformed a raw number pulled shakily from a moving deck into trustworthy data. It was the final, crucial step of processing, a human brain acting as a living computer to account for the atmosphere's curve and the eye's elevation. In this quiet, constant correction, we see the navigator's art at its most refined, a dialogue with reality that acknowledged even the air was part of the measurement. The master navigator's knowledge was his most guarded treasure, a currency more valuable than gold. This was not a skill you could learn from a book or a single voyage. It was forged in the crucible of apprenticeship, a relationship that bound a young student to an experienced pilot for years, sometimes decades. The master was not just a teacher, he was a gatekeeper to a secret world. He held in his memory the precise correction for atmospheric refraction when sighting a particular star low on the horizon from a specific ship's deck. He knew the exact sequence of zenith stars for a chain of islands across 1,000 miles of open ocean. These were not written down, they were whispered, demonstrated, and tested under the open sky, passed from one generation to the next through a sacred chain of trust and observation. This oral tradition created a powerful guild system. By keeping the most precise techniques secret, a master ensured his own indispensability. A ship's owner or a trading consortium could not simply hire any sailor. They needed a pilot who held this celestial cipher in his mind. It granted the navigator immense social status and security, his knowledge literally steering the wealth of nations. But the education went far beyond memorizing star paths. An apprentice learned to read the language of the world itself. He spent countless hours observing the subtle shifts in cloud formations on the horizon, which could hint at distant land or an approaching squall. He learned to interpret the flight patterns of birds, knowing which species would fly out to sea at dawn and return to land at dusk, their vanishing point offering a bearing toward unseen shores. He studied the shape and rhythm of ocean swells, feeling through the hull of the ship how they changed when reflecting off a coastline still below the horizon. The color of the water, the taste of the wind, the gathering of certain types of fog, all were chapters in this living textbook. This was a holistic environmental literacy. The sky and the sea were not separate subjects, they were 2 pages of the same story, and the navigator learned to read them simultaneously. His training was a slow, deliberate attunement of the senses, a cultivation of patience and profound attention. He learned to think in rhythms and relationships, not just in points and lines. A successful apprentice did not just learn to use a tool, he learned to become the instrument himself, calibrated by experience and guided by a deep, almost intuitive connection to the natural world. This was the final human layer over the mathematics of the stars, the wisdom that turned data into successful passage. But the polar sky defied all conventional rules. For Norse explorers venturing deep into the Arctic Circle, the familiar rhythm of day and night dissolved into a single, endless twilight. The midnight sun, that surreal phenomenon where the sun never fully sets for weeks or months, presented a celestial paradox. The very star that had been their primary daytime guide now refused to leave the sky, while the night stars, including their trusted Polaris, hung low and faint, often obscured by a perpetual hazy glow. In this world of constant, low-angle light, the traditional tools of navigation seemed to break. You could not measure the altitude of a star that never rose, and the concept of local noon blurred when the sun simply wheeled in a great, lazy circle above the horizon. To navigate here required not just skill, but a complete reimagining of time and direction. The Norse adapted by turning their entire attention to the sun's endless circuit. They watched its slow, circular path, noting how its position relative to landmarks, or its bearing at what would traditionally be midnight, could still indicate direction. It was a constant, demanding vigilance. Instead of a single noon sighting, they took bearings throughout the 24-hour cycle, mentally plotting the sun's movement like the hand of a giant, slow-moving clock laid flat against the rim of the world. This pushed the principle of solar observation to its absolute limit. They were no longer using the sun as a moving point on a predictable arc, but as a fixed component in a never-setting, rotating sky dome. Surviving in these waters demanded a profound flexibility. The stellar principles remained true, but their application had to be reinvented for an environment that erased the very definitions of day and night. Navigators learned to read the quality of the light, the subtle color shifts in the sky that indicated the sun's hidden position behind the horizon during the polar summer, or the complex twilight bands that served as a compass during the long winter darkness. The Arctic was the ultimate test of celestial wayfinding, a place where the maps written in the stars had to be redrawn by observation and sheer stubborn intuition. It proved that human navigation was not bound by the comfort of a 12-hour cycle. When the cosmos presented a sun that never slept, the navigator's mind learned to stay forever awake, watching, measuring, and finding a path through the world's most luminous and disorienting wilderness. This deep, practical relationship with the stars inevitably bled into the stories we told ourselves. Long before a sailor ever lifted a camel to the sky, he had already learned the constellations from myths told by the fire. In the epic tales that shaped cultures, the stars were never silent bystanders. They were active characters, guides written into the very plot of human destiny. Homer's Odyssey, one of the foundational stories of the Western world, is at its heart a navigation epic. The hero Odysseus spends 10 years lost, and his journey home is punctuated by celestial guidance. He is told to keep the constellation of the Bear, Ursa Major, on his left as he sails, a direct instruction for holding a course. In the story, this is divine advice from the goddess Calypso, but for any Greek listener who knew the sea, it was also plain good piloting. The myth mirrored the reality, granting the stars a narrative power that matched their practical use. They became symbols of hope and home, a promise that even in the deepest exile, a path back existed if you could read the sky. This connection was universal. For the Polynesians, the star cluster known as Pleiades was not just a navigational marker, it was the eyes of the gods watching over voyagers. In Aboriginal Australian Dreamtime stories, the constellations were ancestors who had walked the earth, their forms and journeys etched into the night sky as a lore and a map for the living. The Milky Way might be a river of spirits or a pathway for the departed. These were not just beautiful metaphors, they were mnemonic systems. By attaching a memorable story to a pattern of stars, the vital information of its position and seasonal movement was preserved across generations in an unforgettable form. The dangerous, trackless ocean was terrifying in its anonymity, but if you believed you were sailing under the watchful gaze of an ancestor or following a path laid down by a hero, the voyage transformed. The sea became a landscape with history and meaning. The stars were no longer cold points of light, they were a community of guides. This cultural layer provided a psychological compass as crucial as the wooden one in the captain's hand. It embedded wayfinding into the human psyche, making the immense cosmos feel intimate and purposeful. To navigate by the stars was to participate in an ancient story, to walk a path that gods and heroes had sanctified. It turned a technical act of survival into a spiritual journey where every correct star sight was not just a good measurement, but a sign that you were where you were meant to be. The most reliable number a navigator could pull from the sky was not a simple measurement, but a moment. It was the instant a chosen star reached its peak, hanging motionless for a breath at the very top of its nightly arc before beginning its slow descent. This was the star's Meridian passage, the point where it crossed the invisible north-south line running directly overhead from pole to pole. At this singular moment, all the complex geometry of the moving heavens simplified into a single, clean reading. The star was at its highest possible altitude, its relationship to the horizon frozen and unambiguous. For a navigator, this was the celestial equivalent of a surveyor's benchmark, a fixed point of supreme accuracy. Observing this transit eliminated the errors introduced by trying to measure a star while it was still climbing or already falling, angles that required complicated mental corrections. It turned the chaotic dance of the night into a series of still photographs, each one offering a snapshot of true latitude. Capturing this moment, however, demanded a different kind of skill. It was an exercise in intense patience and focus. A navigator would identify his guide star, perhaps the bright Vega or Arcturus, and then watch it climb. He would use his cross-staff or astrolabe to take a series of measurements as it rose, noting how the altitude increased with agonizing slowness. Then he would watch for the plateau, that fleeting pause where the number on his scale stopped increasing. That was the prize. The star seemed to hesitate, as if offering itself as a perfect reference before continuing on its way. Timing this event was everything. In the dead of night, with no other reference, the navigator became a human clock. He might note the position of other stars relative to the horizon to mark the time, or rely on the turning of known constellations. Later, as mechanical timekeeping improved, the precise hour and minute of a star's transit could be recorded and compared with tables, adding another layer of exactitude. This practice represented a philosophical shift in navigation. It moved away from the constant, anxious estimation of dead reckoning and toward a discipline of waiting for certainty. The navigator was no longer just reacting to the sky, he was anticipating its most generous offering. He learned the schedule of the heavens, knowing which star would culminate at a useful hour of the night. In the vast, trackless ocean, these meridian passages became sacred appointments. They were moments of clarity in a journey defined by uncertainty, a chance to wipe the slate clean of accumulated guesswork and plant a flag of absolute position on the chart. It was the principle that ultimately made celestial navigation trustworthy, the understanding that the cosmos, in its perfect motion, would always present these windows of perfect measurement to those who knew how to watch for them. This stellar certainty created more than safe passage. It forged the arteries of a connected world. With the ability to sail predictable routes across open ocean, the medieval map of trade exploded outward from coastal cabotage. The Indian Ocean, once a daunting barrier, became a bustling maritime crossroads, a Silk Road of the sea. Arab dhows, Chinese junks, and later Portuguese caravels could now rendezvous with seasonal precision in ports from Zanzibar to Malacca, their holds filled with spices, silks, porcelain, and ivory. This was not merely about moving luxury goods, it was about the silent, profound exchange that traveled in the cargo holds and in the minds of the sailors themselves. A navigator from Gujarat might share a refinement to the camel with a pilot from Oman over a shared meal in a Calicut tavern. A star chart painstakingly copied in a Lisbon monastery might incorporate data originally observed in a Samarkand observatory. Celestial navigation created a shared technical language that transcended spoken tongues, fostering an informal global network of practical knowledge. The economic impact was transformative. Local markets, once limited by what could be carried overland, suddenly had access to global demand. The price of pepper in Venice or cloves in Cairo was now set by harvests in the Moluccas and the timing of the monsoon winds whose patterns were read in the stars. This stellar-guided commerce turned isolated economies into interdependent nodes in a vast, humming web. It funded empires and city-states, but more subtly, it financed the very eras of exploration that would follow. The promise of controlling these lucrative, star-charted routes is what drove princes to fund daring voyages down the African coast and eventually across the Atlantic. The navigational techniques honed for trade became the tools for empire and encounter. This is where the story turns complex, for the map drawn by the stars was one of both connection and consequence. The same celestial highways that carried porcelain and astronomical tables also carried profound cultural shifts, new belief systems, unfamiliar technologies, and unfortunately, conflict and hardship. The ability to reliably cross oceans meant that worlds that had evolved separately for millennia were now on a collision course. These encounters, fueled by the ambition that reliable navigation made possible, reshaped societies in ways both celebrated and tragic, weaving a single, often difficult, human story from threads that had once been separate. The stars did not guide us to a peaceful global village. They guided us into the tumultuous, interconnected reality that forged the modern age. They were the silent architects of a new world, one whose benefits and burdens were carried on the same tide. The precise angle of a star was a matter of mathematics, but the act of measuring it was often a matter of faith. Before a Polynesian master navigator, a PWO, would even look to the horizon, he would lead his crew in a ceremony. There were chants to call upon the ancestors, offerings to the gods of the sea and sky, and a deep, communal focus on the voyage ahead. This was not superstition in the modern sense. It was a deliberate ritual to mark the profound transition from the safety of the known world to the immense uncertainty of the ocean. The stars were not just reference points, they were seen as sentient guides, ancestors who had traveled these paths before. To take a sighting without first honoring them was to invite misfortune, to navigate with arrogance rather than humility. The ceremony served a vital psychological function for everyone aboard. For the navigator, it was a moment of intense mental preparation, clearing away distraction and aligning his entire being with the task. For the crew, who would entrust their lives to his readings, it was a visible reaffirmation of his authority and a collective invocation for protection. It transformed the technical act of holding a camel or noting a zenith star into a sacred covenant with the cosmos. This blending of ritual and observation was a global phenomenon. Viking navigators, setting sail into the treacherous North Atlantic, might make offerings to Odin or Thor for fair winds, their gaze shifting between the carvings on their sunstones and the tempestuous sky. Arab pilots, before using their meticulously calculated tables, would often begin with a prayer from the Quran, seeking divine clarity in their measurements. In every case, the ceremony framed the journey. It acknowledged the terrifying truth that all the skill in the world could be undone by a sudden storm or an unseen current. By performing a ritual, the community on the ship was actively participating in their own fate, not just passively awaiting it. It built a shared resolve, a collective courage necessary to sail into a void with only pinpricks of ancient light as a guide. The ritual did not replace the science, it completed it. It provided the emotional and spiritual framework that allowed cold celestial data to be applied with confidence and calm. To trust a star with your life required more than just knowing its position. It required believing you were in a right relationship with the universe it inhabited. The ceremony was how you established that relationship, ensuring that when you finally lifted your instrument to the sky, you were not just measuring an angle, but opening a dialogue. Even the most brilliant star map is powerless against a blanket of cloud. For all their celestial precision, navigators lived under a constant, unspoken dread, the fear of the shrouded sky. When thick cloud cover rolled in for days or a storm system blotted out the heavens for a week, their primary reference vanished. The universe withdrew its guidance, and the ship was plunged into a state of celestial blindness. This was the moment when navigation reverted to its most primitive and perilous form, pure dead reckoning, a continuous chain of guesses with no anchor in the stars to correct it. Every hour in the gray void amplified the margin for error. A slight misjudgment of the current, a wind shift unnoticed in the gale, and the ship's presumed position on the chart would drift further and further from reality, a phantom ship sailing on a map that no longer corresponded to the world. Historical logs from every ocean carry the grim echoes of these episodes. They speak of crews growing desperate as fresh water ran low, their trust in the captain's reckoning fraying with each passing sunless day. In extreme cases, when a ship was believed to be nearing a coast that never appeared, hunger and fear could boil over into unrest. The social order on the vessel, held together by shared purpose and the captain's proven skill, faced its ultimate test. These periods underscored a brutal truth of the age: no system was foolproof. The stars were a magnificent aid, but they were not a guarantee. Their occasional absence was a humbling reminder that the sea remained the final authority. This ever-present threat of failure, the knowledge that a stretch of bad weather could erase all certainty, is what fueled the relentless drive for better methods. It was a race not just for accuracy, but for resilience, pushing navigators and instrument makers to devise tools for the cloudy day, and compelling cultures to develop richer libraries of environmental clues, from wave patterns to bird behavior, anything to piece together a picture when the primary map was taken away. The fear of the blind voyage was the engine of innovation, a stark motivation born from the understanding that the ocean's mercy was always conditional. The whispered secrets of the master navigator eventually found a more permanent home than memory. Knowledge, once guarded like treasure, began its slow migration from the mind of the individual to the page of the book. This shift was subtle at first. The earliest written aids for sailors were not star charts, but practical coastal guides known as rutters, from the French word routier. These were workbooks of lived experience. A rutter might describe a headland as looking like a sleeping giant from the west, note a dangerous reef that appeared only at low tide, or list the best anchorages in a storm. But tucked among these earthy details were celestial clues. A passage for crossing the Bay of Biscay might instruct, steer such that the guard stars of the Little Bear are level with the tip of the mast at the second night watch. This was a stellar bearing translated into a repeatable instruction, a piece of the master's mental star compass written down for another to follow. The rutter was a hybrid tool, blending the intimate knowledge of the coastline with the broader guidance of the heavens, creating a bridge between the security of the shore and the uncertainties of the deep. The true revolution, however, came with the dedicated navigational manual. In the mid-16th century, a Spanish cosmographer named Martin Cortés de Albacar published a work titled The Art of Navigation. This was not a simple collection of tips, it was a systematic textbook. Cortés took the complex, often secretive methods of celestial navigation, the mathematics of solar declination, the use of the Astrolabe and Cross-Staff, the principles of latitude sailing, and laid them out in clear, methodical steps. He explained the spherical geometry of the Earth and the heavens in terms a determined sailor could grasp. This act of compilation and explanation was profoundly democratizing. For centuries, a young man's access to this knowledge depended entirely on finding a master willing to take him on as an apprentice. Now, with enough coin to purchase a book and the literacy to read it, a sailor could theoretically teach himself the core principles. The monopoly of the master pilots' guilds began to crack. Knowledge became a commodity that could be bought, sold, and shared across borders and languages. These handbooks did more than just spread information, they standardized it. When every navigator in the Spanish fleet was working from the same set of tables and the same instructions for correcting a sun sight, their results became more consistent. Shared practice reduced individual error and created a common technical language for an entire nation's maritime enterprise. The handbook became a portable observatory and a master pilot, all bound in leather and stored in the captain's cabin. It was a library of the sky containing not one person's lifetime of observation, but the distilled wisdom of centuries compiled from Arab astronomers, Portuguese explorers, and Mediterranean pilots. A captain sailing from Seville to Veracruz could carry the collective stellar wisdom of the old world into the vastness of the new, a tangible link to the known cosmos as he ventured into the unknown. This transition from oral secret to published text marks a pivotal moment in our story. It moved celestial navigation from an art, dependent on the rare, cultivated genius of the individual, toward a repeatable science accessible to the diligent many. The stars remained in the heavens, but the key to understanding them now also rested on a wooden desk next to a gently swaying lantern, waiting to be studied. That library of the sky, built from countless nights at sea, did not remain bound to the ocean. The very same precision that guided a ship to a new continent became the bedrock for a new kind of voyage, one that would leave the Earth entirely. The stellar catalogues and observational methods honed by navigators were not just practical tools, they were a massive, centuries-long data collection project. Astronomers like Tycho Brahe, whose incredibly precise star maps in the late 16th century revolutionized our understanding of planetary motion, stood on the shoulders of those anonymous pilots who had spent lifetimes measuring altitudes. The urgent need to predict a star's position for a ship's safety drove the mathematics of celestial mechanics forward, refining our models of how the heavens moved. This was not a coincidence. The quest to conquer the horizontal wilderness of the sea demanded a vertical understanding of the universe. Every corrected measurement for atmospheric refraction, every table of solar declination, was a step toward seeing the cosmos not as a mystical dome but as a measurable space. That shift in perception from sky as guide to sky as destination is one of history's most profound intellectual legacies. You can see its direct line today in astronaut training. Modern crews learn celestial navigation as a critical backup skill. If all computer systems were to fail, an astronaut could theoretically use a handheld sextant to sight stars against the Earth's horizon or the Moon's limb and determine their spacecraft's position. It is a sobering and beautiful link to the past, a recognition that the most ancient method might one day save the most advanced mission. More fundamentally, the principles are woven into the very fabric of spaceflight. Planning a trajectory to Mars is at its core an exercise in celestial navigation on a galactic scale. Instead of using Polaris to find a latitude, mission planners use the gravitational pull of the Sun and planets to plot a course, treating celestial bodies as both landmarks and engines. The medieval navigator's mental map of star paths has evolved into the complex orbital diagrams that guide our probes. That sailor, squinting at a star through a wooden cross-staff, was participating in the first draft of a much grander journey. His sky, a map of familiar lights, is now our launch pad. The constellations he used to find a lonely island are the same reference points we use to align telescopes searching for new worlds. This is the enduring truth of the story. The human drive to navigate, to find our place and then move beyond it, did not end when we ran out of ocean. It simply changed scale. We are still measuring the stars not to cross an unknown sea, but to cross the sea between worlds. The courage to trust in distant light for guidance remains our most vital compass, pointing forever outward. A wooden instrument could measure an angle, but only a human mind could decide what to do with it. The final, and perhaps most vital, tool in the Navigator's kit was not kept in a box. It was the quiet, unshakable confidence he carried within himself, a psychological compass that guided him through storms of both wind and doubt. This inner certainty was forged from countless nights under the stars, from the memory of 100 successful landfalls, and from a profound, almost cellular trust in the celestial signs. He had to believe, beyond any hesitation, that when his cross-staff told him he was on a certain latitude, he was. His entire crew's survival depended on that belief. For weeks, even months, they would sail across an empty ocean with no visible proof of progress, their lives resting on the captain's interpretation of numbers pulled from the sky. His job was to project absolute assurance, to make the invisible path feel as solid as a paved road beneath their feet. This was a performance of immense psychological strength. In the privacy of his own thoughts, he might wrestle with uncertainty, recalculating currents in his mind, questioning a cloudy day's dead reckoning. But on deck, his voice was steady, his commands clear. He had to transform abstract celestial data into a narrative of progress for his men, pointing to a swell pattern or a bird's flight as confirmation of their unseen course. This psychological compass prevented panic during the dreaded blind voyages, those stretches of clouded skies when no star could correct their drift. The crew's morale became a resource as critical as fresh water. If they sensed doubt in their leader, fear could spread faster than any disease, unraveling discipline and leading to desperate, dangerous decisions. The Navigator's confidence was the glue that held the entire fragile enterprise together. It turned a collection of anxious individuals into a single, purposeful unit moving toward a shared horizon. This intangible skill underscores a timeless truth about any great undertaking. The most advanced technology, the most precise star chart, is inert without the human spirit to interpret it with courage and conviction. A sextant is a piece of brass. The decision to trust its reading when your life is on the line, that is the essence of navigation. It reminds us that our journeys are never just about the tools we hold in our hands, but about the maps we carry in our hearts, the inner certainty that allows us to steer through the unknown, even when the stars themselves are temporarily hidden from view. That inner compass of confidence was the final star they steered by, a human light as vital as any in the heavens. From the steady gaze on Polaris to the memorized star paths of the Pacific, early navigators performed a magnificent feat. They turned the immutable, distant stars into a dynamic, living map, conquering terrestrial frontiers with nothing but celestial wisdom and unshakable nerve. Their true legacy, however, stretches far beyond the sea lanes they charted. It lives in the scientific curiosity they ignited, a relentless drive to measure, record, and understand the cosmos that would eventually propel us beyond our own world. It echoes in the cultural exchanges that flourished along those star-guided routes, weaving separate continents into a single, intricate story of shared goods, ideas, and knowledge. Most of all, it endures in the sheer human courage they embodied, the quiet decision to trust a sliver of mathematics against the vast, roaring uncertainty of the open ocean. Today, we navigate with the silent beeps of satellites, a constellation of our own making orbiting high above the atmosphere. We plot our course with digital precision on glowing screens. Yet in a profound way, we still sail by starlight. Every global positioning signal, every plotted airline route, every interplanetary trajectory is built upon the foundational principles those early mariners proved with wood and string and patient observation. We stand on the shoulders of those who first dared to look up, not in worship alone, but in calculation, who saw in the night sky not just myth, but mathematics, not just destiny, but direction. Their story is an invitation. It asks us to occasionally lift our eyes from our own modern instruments, to step outside on a clear night, and to truly see that ancient sky map. Can you find the North Star? Can you trace the Great Bear's Bowl? In doing so, you touch a lineage of exploration that connects you to every sailor, trader, and explorer who ever ventured beyond the sight of land. You are witnessing the same celestial clockwork that told them when to turn, when to wait, and when to press on into the heart of the unknown. That shared sky is our deepest, most enduring inheritance. Let their incredible journey inspire your own sense of wonder. What uncharted seas, real or metaphorical, might you dare to cross, guided by your own chosen stars? We would love to hear your thoughts on this epic history in the comments below. And if you enjoyed this voyage through time, subscribe for more journeys into the past, where we continue to explore the stories that shaped our world. Thank you for watching.